Hi, folks. This is Heath. I hope y'all had a fantastic weekend. Um, this is section 13.2. We're going to spend 2 days on this section. So if this video seems a little short, um, it's because there's enough material there's too much material in this video in this section for a 1 day video, and not quite enough for a 2 day video. But I'm going to spread it out over 2 days. So we're going to go through today's video. A couple of other things that I want to mention is that you do have some WebAssign problems to look at. Um, and so don't get behind on those. And the other thing that I want to mention is that I appreciate the feedback that y'all gave me on last week's survey. You've made some suggestions on things I am doing well. I appreciate those. Y'all are very kind. And some things that I can do better. And I've responded to those suggestions. Some of them I have implemented, and some of them I've given reasons why it's not feasible, or it's difficult, or why I'm not allowed to implement them. And so if you want to see the feedback for the survey, they're on Canvas. You just have to scroll down below today's notes, and then you'll see a link to the survey feedback. All right, let's go ahead and get started. Say we have a function, a vector function that has an x-coordinate and a y-coordinate, and maybe many coordinates. We could have a vector with a lot of coordinates to it. If each of the individual coordinates is differentiable, then the entire function is differentiable, and the derivative of the vector function is just the derivatives of each of the individual functions. This is exactly what you would expect to happen. And so there are no surprises here. So let's try an example. Okay. I want to compute the derivative of this function here. So I take the derivative of the first part, and I get 2t minus 5. Then I take the derivative of the tangent part, and I get secant squared of t. The third part is a little bit tricky. I have to take the derivative using the chain rule. So I get 2t to negative 1/2 power times 2. And then that turns out to, actually it's 1/2 2t to the negative 1/2 power times 2. And there's a little bit of simplification that happens here. This is 2t minus 5, secant squared of t. The 2's cancel, and we get negative 1 over root 2t. All right. Okay, let's move on to the next example. Let's apply this and find the parametric equations for the tangent line to this curve. Okay. So one of the things we're going to need the derivative of this vector function, which is 2, 6t, 2t minus 3. And now we're going to have to figure out what happens at this point. There is a common mistake that people make here. And so I'm going to go ahead and tell you what that mistake is and ask you not to do it, is to plug in these coordinates in to this point. To plug in 2n for x and 3n for the y-coordinate, and negative 2n for the z-coordinate. And say that the derivative is 6 times 3 would be 18, and 2 times negative 2 minus 3 is negative 4 minus 3 is negative 7. That's wrong. Don't do this. And here's why it's wrong. What you're saying is that the time is 3, and you're also saying that the time is negative 2. This t and this t are the same variable that comes from over here. What we have to do instead is figure out what time gives us 2, 3, negative 2. So 2t is equal to 2, and 3t squared is equal to 3, and t squared minus 3t is equal to negative 2. And this happens when t is equal to 1. And so the time that this point is generated is time t equals 1. And so we use the time at t equals 1 to create this. And this is going to be 2. 6 times 1 is 6. 2 times 1 minus 3 is negative 1. And that's correct, and this is wrong. Okay? So don't take this point and just plug it in directly without solving for t first. Okay? Now, this is not the answer. The question is looking for parametric equations. But they're equations for a line. And we know what that should look like. The equations for a line look like m times t plus b. They look like mt plus b. And m is the slope. Well, we know what the slope is because the slope comes from the derivative. So the slope is going to be 2t plus b. In the y-coordinate, we're going to have 6t plus b. And the z-coordinate, we're going to have negative t plus b. But where does the b come from? Well, the b has the intercepts. But we know that the tangent line starts at this point. And if we assign t equals 0 to that point, 2 times 0 plus b is equal to 2. And 6 times 0 plus b is equal to 3, and negative t plus b is equal to negative 2. And so the point, 2, 3, negative 2, gives us our b's. This gives us b, and this gives us m. Okay? And so once you have the derivative vector, then it's really easy to write out these parametric equations. Okay? All right, let's move on. When we talk about the unit tangent vector, this is the tangent vector, which is the derivative of all these coordinates, made into a unit vector. And the way we make a vector into a unit vector is we divide by its magnitude. And so when we talk about the unit tangent vector, we talk about the derivative divided by the magnitude of the unit tangent vector, divided by the magnitude of the tangent vector. Let's do an example. This example is just in 2 coordinates. Find the unit tangent vector at the point negative 2, 2. So the derivative is 4t, comma 2t plus 1. Okay? The time is whatever time makes this point happen. So to find the time, we have to set 2t squared minus 4 equal to negative 2, and t squared plus t equal to positive 2. Let's add 4 to both sides over here, and we get 2t squared is equal to positive 2, and so t squared is equal to 1, and so t is equal to plus or minus 1. Well, plus 1 over here checks. 1 squared plus 1 does equal 2, but negative 1 doesn't check. Negative 1 squared plus negative 1 is equal to 0. And so the only time that works is time equals plus 1. And so that tells me that the derivative at time equals 1 is 4 comma 3. But the magnitude of that derivative is the square root of 4 squared plus 3 squared, which is equal to 5. And so the unit tangent vector, which is usually written as a bold capital T, you'll also see people who are on a computer where they can't do bold, write it as a T with a little hat over it. Either one is the vector 4/5, 3/5. Is this vector divided by this number. Okay? And we call that the unit tangent vector. All right, let's keep going. When we want to take the antiderivative of a function, we're taking the antiderivative of a vector function that has multiple components to it. Let's say there's a third one here. Well, when we take the antiderivative of this function, we get, some antiderivative capital F1 plus C, and then we get some antiderivative of this function plus C, and an antiderivative of this function plus C, except these are all different C values. We get a constant of integration for each component, and they might all be different. And so that complicates things a little bit because we have multiple constants to solve for, but it's not too bad. Let's look at an example. Suppose the derivative of r of t is equal to this function here, and r of 1 is 3, 3, 5. Okay? So what we want to do is integrate the vector function 2t, 4, 2t minus 1 dt. The integral of 2t is t squared plus a constant. The integral of 4 is 4t plus a constant. And the integral of 2t minus 1 is t squared minus t plus a constant. At time 1, r of 1 is equal to 335. So 1 squared plus c1, 4 times 1 plus c2, and 1 squared minus 1 plus c3 adds up to 335. And so 1 plus c1 is 3, so c1 is 2. 4 plus c2 is 3, so c2 is negative 1. 1 minus 1 is 0. 0 plus c3 is 5, and so c3 is 5. And so for my final answer, I get the vector t squared plus 2, 4t minus 1, and t squared minus t plus 5. Okay? All right. So let's move on and look at this last example. If we're doing a definite integral, then the plus c's go away and we don't have to worry about the plus c. So this is the same vector function as from the last example, but we're taking a definite integral from 1 to 2. And so the definite integral from 1 to 2 is the vector that contains a definite integral from 1 to 2 of 2t dt, followed by the definite integral from 1 to 2 of 4 dt, followed by the definite integral from 1 to 2 of 2t minus 1 dt. Integral of 2t is t squared, but we have to evaluate it at 2 and 1. 4t, which we have to evaluate at 2 and 1. And t squared minus t, which we have to evaluate at 2 and 1. So when we plug in 2, we get 4. 4 minus 1 is 3. When we plug in 2, we get 8. When we plug in 1, we get 4. 8 minus 4 is 4. When we plug in 2, we get 4 minus 2 is 2. When we plug in 1, we get 1 minus 1 is 0, and 2 minus 0 is 2. And so we get this function here, this vector here. All right? So what we've covered today is taking derivatives and antiderivatives of vector functions. If we go back to the model we were thinking about on Friday of thinking about a vector function as representing a trajectory, then the derivative represents the velocity of the trajectory. The second derivative represents the acceleration of the trajectory. And what we're going to look at next time are problems that involve solving for velocity and acceleration position. If you have some of the information, how do you solve for the other parts of the information? We've seen the core methods of how to take derivatives and antiderivatives. What we'll be doing next time is applying that to thinking about this in terms of velocity and acceleration. All right? Have a great day. I'll see you guys on Wednesday again. Take care.